Hello, everyone. Again, these are the answers to the AP problems that I gave you on the Friday before break. I believe you should be okay with the majority of these. I want to talk about these 4 problems I have circled. So looking at number 4 off of pages 45 to 49, we are given f of x is equal to the quantity 2 plus 3x to the 4th. And we are asked to find the 4th derivative. So let's carefully go through this. Definitely have to use a chain rule. So our first derivative becomes 4 times the quantity 2 plus 3x to the 3rd times 3. Now, if you took a look at how the answers were written, I'm actually just going to leave it written this way. But we could technically put the 3 in front. So we could show 4 times 3 rather than saying 12. And then it's 2 plus the quantity 2 plus 3x cubed. So now if I were to take the derivative of this, our second derivative, the 3 is going to come down in front, so it becomes 4 times 3 times 3 times the quantity 2 plus 3x squared times another 3. So now this becomes 4 times, we'll say 3 cubed times the quantity 2 plus 3x squared. Our third derivative, now the 2 will come down in front, so this becomes 4 times 3 cubed times 2 times the quantity 2 plus 3x to the 1st times another 3. So we could write this as 4 times 3 to the 4th times 2 times the quantity 2 plus 3x. And then now our fourth derivative, we're going to write that notation like this. So now this becomes 4 times 3 to the 4th times 2, and then we have the derivative of this, which is just going to give us 3. So now we just have to match, see which ones are equivalent here. Now these answers had a little exclamation point. So when you see like this 4 and exclamation point, this is 4 factorial, which means 4 times 3 times 2 times 1. So can we write this using a 4 factorial? Because other than the first answer A, which is 0, they all have a 4 factorial. So technically, yes, I could write this as 4 times 3 times 2, technically times 1, times 3 to the 4th. So this whole first part is 4 factorial times 3 to the 4th, which gives us C. All right, let's go ahead and take a look at number 7 off of the same set of pages. Okay, so number 7, we're given the limit as h approaches 0 of the absolute value of x plus h minus the absolute value of x all over h. We want to determine this at x equals 3. Well, rather than using the limit notation, we know that this whole thing is really equal to f prime of x. But we have to figure out what f of x is. So if you recall, f prime of x is equal to f of x plus h minus f of x all over h. Forgot the limit notation. Limit as h approaches 0. So right here at the very end, that's our f of x. So if I go and I look up here, so f of x is equal to the absolute value of x. Now in one of the lessons, I forget which day I made it for, it could have been that Wednesday or that Friday before break, we derived the derivative for the absolute value of x function. So here we would have f prime of x So yes, this was y prime or f prime of x was equal to x over the absolute value of x. So now we would say f prime of 3 is equal to 3 over the absolute value of 3, which is 3 over 3. So this is 1. And that correct answer was C. All right, now from pages 77 to 78, let's take a look at that number 7. So in this problem, we're given a piecewise function for f of x. We want to let f be the function defined above, where c and d are constants. If f is differentiable at x equals 2, what is the value of c plus d? So let's analyze this statement here. We know for a function to be differentiable, it is not going to be one of the 4 types of non-differentiability. So we're not going to expect a corner, a cusp, a discontinuity, or a vertical tangent. So I want to go back to one of those. So we're not going to expect a discontinuity. This means that f is continuous at x equals 2. Now remember, for a function to be continuous, f of 2 is going to exist. The limit of f of x as x approaches 2 also exists, meaning the left-hand limit is going to equal the right-hand limit, and the f of 2 is going to equal the limit of f of x as x approaches 2. So just to kind of separate this here to review what it means for a function to be continuous. So now that we have a continuous function at x equals 2, so since f is continuous at x equals 2, these two expressions are going to be equal to each other. So cx plus d is going to equal x squared minus cx at x equals 2. And now since x is 2, I could substitute the 2 in. So I'm going to get a 2c plus d is going to equal 4 minus 2c. But this, I still have 2 variables here, so I'm going to leave it here for a moment. And I'm also going to go ahead and write out the derivative, a formula for the derivative, just like what we were looking at for the quick review number 12b. We would say f prime of x is going to equal, since c and d are constants, the derivative of cx plus d is just going to become c for x is less than or equal to 2. And then the derivative of x squared minus cx becomes 2x minus c for x is greater than 2. So again, since f is continuous at x equals 2 and differentiable at x equals 2, we could also say that c is going to equal 2x minus c. So I'm just going to kind of put arrows here. Because of those 2 facts, I also know that c is going to equal 2x minus c. So the derivative is also going to be continuous at x equals 2. So I could set those 2 expressions equal to each other. And then again, at x equals 2, I'm going to get c equals 4 minus c. So 2c is going to equal 4. Solving for c, I get c is equal to 2. Now I'm going to bring this back over here. If c is 2, I'm going to get 4 plus d is going to equal 4 minus 2 times c will give me 4. So 4 plus d is going to equal 0. D is going to equal negative 4. So I have my values for d and c. Therefore, c plus d is going to equal 2 plus a negative 4, which is going to give us negative 2. And now let's go ahead and take a look at number 9. Here we're given h of x is equal to g of x minus f of x. And we're also given a table of values. We want to know what h prime of 2 is. So let me write out these values here for a second. Okay, so here's the table that we were given in the problem. So first let's go ahead and write out what is h prime of x. So we're going to use a chain rule here. So it's a derivative of the outside. So it's g prime of x minus f of x times the derivative of the inside. So we're going to get derivative of x is 1 minus f prime of x. So now h prime of 2 becomes g prime of 2 minus f of 2 times 1 minus f prime of 2. So I still have to leave this g prime here. 2 minus f of 2. So f of 2 is 3. So we get a 2 minus 3. And then 1 minus f prime of 2 is negative 1. So now we get g prime of negative 1. 1 minus the negative 1 becomes 2. So now we're looking at g prime of negative 1. That's going to give us a negative 3 times 2 gives us a negative 6. So that answer was A. So if you guys have questions on any others, please join the Zoom meeting later today or email me, and I'd be more than happy to go over those with you. So now we're going to continue with section 4.1. We're going to take a look at a theorem involved in this section called the extreme value theorem. So pause the video to copy this theorem down. Now, with most theorems, if a hypothesis of the theorem is met, then we're guaranteed to get to the conclusion. So the extreme value theorem is a guarantee that we're going to see, or we're going to have absolute maxes and absolute mins if f is a continuous function on a closed interval from a to b. So if that holds true, then f is guaranteed to have a maximum value, an absolute maximum value, and an absolute minimum value on this closed interval. So we're first going to take a look at some graphs from the textbook. But again, pause the video if you still need more time to copy that down. All right, we're going to take a look at 3 graphs, problems 2, 4, and 6 off of page 184. Here we're going to identify each x value at which any absolute extreme occurs. So we're going to write it the same way we were writing all of our answers for gift 4.1. We're going to explain how our answer is consistent with the extreme value theorem, meaning we're going to just answer yes or no if the extreme value theorem conditions are met. So let's first answer this here. For number 2, is the hypothesis of the extreme value theorem met? So if we take a look at f of x, we notice this is a continuous function, and it is on a closed interval. So yes, f is continuous on a closed interval. So we are guaranteed an absolute max and an absolute min. So let's go ahead and find them. Our absolute max would occur at the highest y value point. That happens when x is c, so that would make this f of c. So we would say our absolute max is y equals f of c when x equals c. We're also guaranteed an absolute min. Now, if it doesn't happen between the x values of the endpoints, it could happen at the endpoints themselves. Well, a is not an absolute max or min. It would be a relative if we were comparing it here. But over here, when x is b, that would be our absolute min. So that occurs when x is b, our min would be f of b. So our absolute min is y equals f of b when x equals b. Let's take a look at number 4. Again, let's answer our question about the extreme value theorem. Are we on a closed interval? And in this case, because we have open endpoints, no. Is this function h of x continuous? Also, no. So we would say no, the conditions for the extreme value theorem are not met. H of x is not continuous. Also, this is not on a closed interval. H of x is not on a closed interval. However, just because the conditions for the hypothesis aren't met, that would mean it's a guarantee. But if it's not met, there still could be a possibility for an absolute max and an absolute min. There's just no guarantee. But if we take a look here, there are no maxes and min values that we're looking at here. So no absolute max, no absolute min. Because they're open endpoints, we're getting closer and closer. There's an infinite number of x values that we're looking at here, so there's no definitive final endpoint there that's the highest or the lowest. Now I do want to take a look at number 6. Again, let's answer the question about the extreme value theorem. Now if we take a look here, we do have a closed endpoint when x is a, and it is disconnected here, so but we still have a closed endpoint here at f of a. So technically, yes, this is a closed interval. However, g of x is not continuous. We have to jump up here. So the extreme value theorem conditions are not met because g of x is not continuous. However, there still could be a possibility for an absolute max or an absolute min. Hopefully, if you notice right here, here's our lowest point. So we do have an absolute min. This would give us f of c. When x equals c. Now, because we're on a closed interval, even if we don't have an absolute max in between the two x values, we do have one at the endpoint. So right here, that is the highest y value that we get. So that's f of a. So in this case, we do have an absolute max, which is y equals f of a when x equals a. But these weren't a guarantee because the extreme value theorem hypothesis was not met. All right, now when we're asked to do this analytically, we want to show algebra, we want to use calculus. So here we want to find the absolute extrema and where they occur. So our function is g of x is equal to e to the negative x. And it could be written like this, but this is indicating a closed interval, so this means the same thing. So we are on a closed interval. Now we do know the function y equals e to the x, y equals e to the negative x. We've worked enough with these exponential functions here to know that it is continuous. So the extreme value theorem is met. We are looking at a continuous function on a closed interval. So what we're going to do first is find our first derivative. So if you remember the derivative of e to the x, it's still e to the x times the derivative of x. So this becomes, in this case, e to the negative x times a negative 1. So we're getting negative e to the negative x as our derivative. So really, this is the first step we want to write out. And yes, we can explain why. So even though we answered it yes, we would say g of x is continuous on a closed interval. Step 2, we want to go ahead and find the derivative. Step 3, we want to ask ourselves 2 questions about this derivative. Is g prime of x ever equal to 0? If so, what are the x values? So we want to find the critical numbers. Is g prime of x ever undefined? So again, these 2 questions help us find our critical numbers. So let's set negative e to the negative x equal to 0. Or we could say e to the negative x if that will ever equal 0. So if you picture the graph of this, that's fine. But we could still use algebra to help us out. We could do what to both sides, guys? We could take the natural log of e to the negative x is equal to the natural log of 0. Now this will just become negative x times the natural log of e, which is 1, is equal to the natural log of 0. But real quick, go ahead and type in the natural log of 0 on your calculator. It's undefined, isn't it? So here we would just get no solution because of this part right here. So in other words, and again, picture the graph, y equals negative e to the negative x. That's never going to equal 0. So it's never equal to 0, and it's also never undefined. So we have no critical numbers, and that's okay. If we did, we would just include them in our table. So step 4 is to make a table. So we're going to have x, we're going to have g of x. What numbers are we going to include in our table? Well, if we had any critical numbers, we would. But we also need to include the 1 and the negative 1 from the endpoints of the interval. So in this case, we want 1 and negative 1. So again, g of x is equal to e to the negative x. So g of negative 1 becomes e to the opposite of a negative 1. So that just becomes e to the first, or e. And then g of 1 becomes e to the negative 1, or 1 over e. So we could write this out now. We know that 1 over e, the reciprocal of e, is definitely going to be smaller than e. So we would say that the absolute max is y equals e when x equals -1. The absolute min is y equals 1 over e when x equals 1. So let's check this on our calculator. Go ahead and graph y equals e to the negative x, but then adjust your window settings. Make your x min -1, make your x max +1. Go ahead and pause the video if you need more time. So here we're looking at the graph. Now you could do the graph trace. You can go ahead and do menu 5(1) and then type in -1. It's going to take you to this. So when x is -1, that is our highest point. And then over here when x is 1, we should be getting 1 over e, 1 over 2.7 roughly. But you could just see nothing happened in between. We had no critical numbers. So the absolute max and min occurred at the endpoint. So we're on a closed interval. We're a continuous function on a closed interval. All right, so this assignment is due Thursday. Please do page 184, exercises 1 through 17 odd. Be sure to skip number 7. And then AP practice off of page 17, please do number 21. As always, guys, take care. Let me know if you have any questions.